All right.
Why didn't we?
Lynn?
Yeah, why didn't we listen to
All right. I've
Yeah, we didn't need it.
didn't need it. All right. Those of you from Block 3 that might be watching this, I apologize because I forgot to start the recording. Okay. So here we are. So this is a height. So one thing we could do to get number 20, does it reach the height of the metrodome? We could just graph this height equation. We put a 110 in the initial height and see, and sure enough, at the peak, it does hit 194. But the calculus thing that we will be doing a lot of as we go on is what happens to the slope at the peak? What's the slope? 0, right? At the peak, the slope is 0. Well, we have an equation for the slope, don't we? Right here. The slope is the v equation, the h prime equation. And that is 110 minus 32t, correct? So let's say we just had a TI-30 calculator. We did not have a graphing calculator where we could easily graph that parabola. What we could do is we could set this velocity equal to 0, correct? That would give me the time that the velocity is 0, which wouldn't that be this time right here? So that's a pretty easy one to solve. We get this, right? So do it for me real quick. What's 110 divided by 32? 3.4 something. And then take that number and plug it right back into the height equation, right? And that would tell us how high the ball got at its peak without drawing a graph, right? So setting the velocity equation equal to 0 would tell us when it hit its high point, because its high point, it stops. Well, in this case, it's going to hit the ceiling before it gets to its high point, right? But we can tell what its high point would be. When it hits its high point, we plug that back into that other one, and you should get that 195 number that you were talking about. Right? All right. That is something that we will do a lot. As a matter of fact, when we get into some problems later on, kind of the line to remember will be, if you don't know what to do the derivative and set it equal to 0. Because that's a very common thing. When the derivative is 0 means the slope is 0. And that's a very interesting point to us because that's what happens at peaks and that's what happens at valleys, at maxes and mins. The slope is 0. So setting the derivative equal to 0 is usually a point of interest for us. Okay? So that's just a little peek into what we might be doing with something like that. All right, let's go onward. I don't know why I was doing that. Okay. What was the next one? 25. Okay, 25 was the speed limit law. They said that h of 0 was 0. Is that right? And is that what they told me? Yeah. And that h prime of x is always less than or equal to -2. Now that means it could be -3, -4, -5, right? Those kind of things. So that means that's the slope. So that means I could be going over 1, down 2. Or maybe over 1, down 3, or over 1, down 4, right? That's what I've learned from this right here. So they first asked me, is it possible that h of 5 is less than or equal to -10? Is that correct? Okay, so we look at this, we got the h graph right here. We start at 0, 0, and they're asking me about h of 5. So if I go over 5, okay, so here's the h graph right here. I go over 5, I know I've got to go down 10. It's the only way I can have a slope of -2. Now the slope could be -3, -4, and so forth, so I might even go down farther, right? So h of 5 definitely has to be below -10, less than or equal to -10. So how would you explain this on a quiz? You would probably draw that picture and then write a few sentences like what I just said, right? That's how I would explain it. Okay, now you've got part B. Or is it, I think, is there a part B? Part B says show that h of 3 is less than or equal to 5. Is that what it is?
Yeah.
5? Well, 5 kind of looks like a 2. Kind of backwards, upside down, whatever. All right, so if I've got 0 here and I'm going to go over to 3, According to what this says, that if I go over 3, the h-graph has to do what? Has to go down at least 6. Right? So I know that the h-graph, or I know that h of 3 has to be less than or equal to -6, correct? So, is it true to say that h of 3 is less than or equal to 5? Certainly. If it's got to be less than or equal to -6, it's definitely less than or equal to 5. Right? It doesn't have to be. It's an or. Or means it could be one or the other, right? So it's, again, same thing. I've got $5 in my pocket. Is it true that I have less than or equal to $1 million in my pocket? Yes. Right? I can say less than or equal to. It's true that I have less than or equal to $1 million. Okay? So, is it less? And I knew that would throw some people off. That's why it's a good problem. Less than or equal to 5? Yes, definitely. Not only that, it's less than or equal to -6. So, it's definitely got to be less than or equal to 5. All right? And then did it say something else there?
Yeah.
Car talk. Okay, so let's turn this into, instead of slope, let's turn this into miles per hour. Right?
You didn't do that.
That's some kind of car, I guess. But that's miles per hour. And so let's talk about this in terms of east and west. Right? So what is this? The car is going 2 miles an hour in the westerly direction, or could be -3, or could be -4. So what's that mean as far as the speed? Could be faster, right? -3 is faster. -4 is faster, yeah. But all negative, so it's in the westward direction. So this is saying the car is going at least 2 miles an hour to the west. But it could be going faster. Now this means this is your starting point. So that's Bismarck. Remember we were talking about Bismarck yesterday. So that's Bismarck. And so were we supposed to explain which one? A or B? Both. Okay? So what does this one say in car talk? This says 5, what would the 5 be? 5 hours. In 5 hours, no, you're not, no, this isn't miles per hour. Now this is just H.
He's less than or
This is just miles. So in 5 hours, he's at least 10 miles west. Yeah, he's,
Yeah,
What's
because,
that?
Because when you said car talk,
we figured how you would explain it to someone if you were in a car.
not necessarily.
Like small talk.
Yeah.
I have like small talk.
Like I figured it was taking A and B and putting it into a paragraph. Yes, now you realize why we're laughing so hard.
that's a first. I
I
gotta
feel
admit.
like that shouldn't be a first. Like, I feel like
That's a-
everyone would do that.
Really? Okay.
Yeah, that's ridiculous.
All right.
If they would have said put it in
Rate of
miles per
change.
hour
Yeah, you're right.
in miles.
Yeah.
That's
The,
car talk.
the authors of this book do have some interesting ways of saying some things, which most of the time I like. I kind of like this one. Car talk does mean in rate of change mode. Okay. All right. So anyway, did anybody else think that? Okay. All right. So,
I was thinking miles per hour.
yeah. Okay. Yeah. Silly us. All right. So at 5 hours, you guys. I guess. So I'm glad I've recorded that too. I guess. So at 5 hours, if they're going 2 miles an hour in a westward direction at least, or faster, then at 5 hours they have to be at least 10 miles west. Okay, so that's an easy one. Now, again, this one, the second one gets a little trickier. Same thing, they're going at least 2 miles an hour west or faster. So at 3 hours, they have to be less than or equal to. Now think of a number line here. If I'm at 0, east is this way, west is this way. What's less than mean then? Less than means west, right? So less than really means west, okay? So this is saying at 3 hours, you have to be west of 5 miles east, okay? So think about that. If I'm heading, so if this car, so here's 0, I'm going 2 miles an hour west for 3 hours. We know that means I have to be at least 6 miles an hour west. But the question is, are you, at 3 hours, are you west of 5 miles east? Yeah, definitely. Because you didn't even go east. So you're definitely west of, but that's how you have to interpret this in that language.
That's exactly how you explained it.
You just didn't put it in a
You
miles
just-
per hour.
Okay. Well, then, okay. Well, then you were maybe on that. All right. Let's talk about those graphs on 35, 37, some of those.
32, 35.
32, 35. Now,
Do it.
there were a few people I talked to this morning, and so about some of these things. Let's run through this again. What I like about these problems is it really makes you focus on this idea of slope. The slope of the position graph is the y's of the velocity, and the slope of the velocity is the y's of the acceleration. So a problem like this can really make you, some of the graphs I saw as I went around were pretty good. Some of the graphs were just kind of thrown together, and I'm not sure how much thought went into it. So we got to really focus on that. So we got position, velocity, acceleration. Now remember, position prime is the velocity, and velocity prime or position double prime is the acceleration. Okay? So the first one, now they said the time is positive. Okay, the first one just says the car leaves the origin, or the car, whatever, the object, leaves the origin at a constant velocity. So what do you got? It's got to be a line, right? Got to be a line. Now, did it have to go up? Could it have went down? Could it have went down? It could have went down. It just said leaves the origin. Didn't say if it was going east or west, right? Whatever. Does it have to be straight? Does it have to be a line? Definitely, because it said constant velocity. Since it's a constant velocity, it has a line. Now, I might make a comment about straight line. We don't really have to say straight line, right? Because lines are always straight, right? If it's not straight, it's curved, okay? So slope 0 is a horizontal line. Yeah, I think that's what a lot of people mean. When they say straight line, I think they're thinking horizontal line, right? All lines are straight. A bent, it's not a line. If it's bent, it's not a line.
It doesn't exist, John.
It could be an angle.
I'm not sure what
It could be
bent
an angle.
Where are you looking for?
Parabola.
That's two line segments. That's piecewise. That's two line segments. Okay?
We understand.
All right. So
No clue.
this could have went down, right? It could have done this. We could have had one going this way. It didn't say that what direction, but it has to be a line, okay? And it has to go away from the origin. And it couldn't be horizontal, right? It has to have a slope, either positive or negative. So the velocity would simply be the slopes of that. Well, the slope of this is what? Some constant positive number. So the drawing of that would have to be just a horizontal, right? Unless it was this dotted one, then it would have been down here, right? Because this slope is like 5, so you would just plot 5, okay? And the acceleration has to be what? No, well, yeah, but
0.
it's got to be 0. Because the graph over here has got to be the slope of this. So that's got to be 0, okay?
Yeah, we didn't get on this.
All right, let's go to the next one. All right. Now, what's the next one? 35? Okay, 35 said that what? It went left then, or right then left. Right then left, which makes a difference, right? Right then left. So right would be positive, left would be negative in position and so forth. So could this graph have just went up like and been a V? Okay? Would it have to have been that? It would not have had to have been that. It could have done this. It could have been curved, right? That would be right then left. Now it matters because which one of those you chose is going to change what your next graph looks like. Okay? All right. So let's say you chose this as an option. What would be the velocity graph? Well, in the beginning, what's the slope? Positive and constant. So it's got to look like that. Then when it gets to this point, it's negative and constant. So it's got to instantly change to that. Now, right? Now, here's something, this is very important today. This idea right here, when we have a sharp point on a graph, we say that the derivative or the slope is undefined at that point. There is no slope at this point. It is not a 0 slope. And you think about it from a physical perspective, this really couldn't happen. Because what you have is the object going at a constant velocity and instantly changing the other direction to a constant velocity with no slowing down or speeding up, right? So from a physical standpoint, you wouldn't have this, but that's why there is no velocity at that change. That's why it's undefined, okay? So this, typically doesn't have it, but we will have functions that have sharp points, and there's not really a good technical term for those. That's what we'll say, sharp points. If you have a sharp point, a sudden change in slope in a graph, or an instantaneous change in slope, then we say the slope's undefined there. So you probably should have open circles, right there, like that, if that's what you have. So you got a positive constant slope switches to a negative constant slope. Now what would the acceleration look like then? It'd be 0 and then stay 0. You might say there'd be a hole there or something at that one point where there was nothing. Okay, now on this one, but now it totally changes if you're over here. Okay, what's the slope here? I mean, at the beginning, now here's this thing I was drawing the tangent lines. This is where those tangent lines become important. The slopes are positive slopes in the beginning, but what's happening to them? Getting smaller. In other words, I usually like to put numbers with it. To me, this is a 4 slope, a 3 slope, a 2 slope, a 1 slope. Does that make sense? So the slopes are 4, 3, 2, 1. So that means over here I'd want to plot a 4, a 3, a 2, a 1. So I would want to start up here, and it would want to come down to a 0 slope, which is what you have at the peak. Right? Now the question is, would that have to come down as a line, or could it curve as it comes down? It could curve. Now if it would have said that it moves right and then left, and it said something about at a evenly changing velocity or something like that, then it would probably be straight. Then the velocity would be at a constant rate of change, and so then it might have been straight, okay, or a line. But they didn't say that, so you could have had this come down here curving. All right, now what do we got? We got negative slopes. They're getting more negative. You got a -1 slope, -2, -3, -4, right? Negative getting more negative, which means your y values here have to be negative and get more negative. So it just continues on. So it would just be a line like that. Now again, it could have curved. It could have come down here kind of in an S shape. This graph could have kind of come down and then curved and done that. And that would have been accepted. We just don't have enough information to know. Okay, let's say it was this line. Then what would I have over here? Remember, over here I'm going to plot the slope of this. Yeah, it would just be a negative line down here, right? Because this is a negative constant slope. But say that line's a -3 slope. So you would graph -3 on the other, and so it would be horizontal. Okay? So you're plotting the slopes of each graph that you draw. All right, 37, was that the last one? All right, what did that one say? That one's probably easier because I don't think it has many options. Moving towards the origin at a steadily increasing rate. So this one's got to start away from the origin and come down at a steadily increasing rate, meaning going faster and faster and faster. So it's got to be getting steeper. It's got to be getting steeper because it's going faster and faster. Okay? And again, same thing. Let's say it starts at a 0 slope. Now we don't know it started at a 0 slope. Didn't say that, right? But let's say my picture is. And so this would be like 0, -1, -2, -3. So my graph here would be going down like that, right? Now, if your curve didn't start at a peak, if your curve didn't start at a 0, then this graph might not start at a 0. It might have started down in the negative. It just depends how you do it. But since it said it was steadily increasing, that has to be a line. We don't have an option. And then this one would just be negative downwards, negative horizontal over here. Okay, because it's a line. All right, so we're seeing the use of these terms like increasing, and we're getting the, hopefully the idea of looking at a graph, looking at its slopes, and thinking about plotting those slopes. Yes. Okay. All right, 41. Says H, what's it talk about? It talks about the H function, which is the hours of daylight, I think. Is that what it said? Or the time between time between sunrise and sunset, which that's hours of day, right? So you can say it either way, the way they said it, or hours of daylight would be good. And so that's what H of T is. Hours of daylight, T days after January 1. Okay? And so what was the first question they answered? What was the first question? Of how much? Okay, what does that mean? This will definitely be on the next quiz, where you have a description of a situation, just like we did with position and velocity the other day. Okay, Josh, what do you think? Yep.
Okay. I put that at these hours past 5 point.
100 days. In this case, it's days.
Yeah. That the slope is 25 meters. Oh, this is for D. Okay. That would be D.
Hold on. Let's do this one. Okay. Now, I wouldn't use slope. I wouldn't use the term slope here because we're in context of a problem. So, Zane?
The change in daylight between one day and the next.
Okay, but let's be more specific. I mean, yeah, it's not a very big number. Use that number. Use 0.05, and you say from one day to the next. So I would say from the 99th day to the 100th day. And that's a good way to do it. Is in business they call that marginal profit. We use derivative. They talk about the profit on the next book we sell or whatever. So one way to say is on the 100th day. But I still haven't heard enough about the 0.05. What's that telling me? What's increased? The daylight has increased 0.05 hours. Now you can multiply that by 60. I don't know what that is. 3 minutes. 0.05 times 60. Is that 3? I think it's 3. So that'd be 3 minutes. Okay. So 0.05, we could say 0.05 hours. Or we could say 3 minutes. Okay. Because that'd be, so on the 100th day after January 1st, there is 3 minutes more daylight than there was on the 99th day, because that's as instantaneous as we can get when we're talking about days, right? So to say, or you could just say this. You could say on the 100th day, the hours of daylight have increased by 0.05 hours. If you said that, that would be fine. Now, why do we say increase? Because that's positive, right? If that was negative, we'd have said decrease. So 100 days after January 1, the hours of daylight have increased by 0.05 hours. That would be a great answer. Okay? Great answer. So now in B, it says, when is H prime less than or equal to 0? Now that really means negative, right? So when is H prime negative? Okay, go.
Well, 174 days is like 5.6 months.
Okay.
5.6 months away from January is like the winter months.
Okay.
So from that point to January 1st, the days are shorter.
Where'd you get 5.6?
From 174.
Where'd you get 174? It does? Well, it might somewhere. It might in the back.
Alright, 171.
171. Where'd you get that?
Yeah, I don't know how I would know.
I just looked at the back and then explained that because I didn't know.
Okay. All right. So let's talk about how we would get it without looking at the back. So no, I mean that's fine. I mean that's okay. But I'm just But I'm just saying. Okay. What do we say H prime is? H is hours of daylight. Now listen. H is hours of daylight. Okay. So what's H prime? The change in hours per day, hours of daylight per day. Remember, it's a rate. So it's change in hours of daylight per day. So if it's negative, what's that mean? The days are getting shorter, right? The hours of daylight, if H prime is negative, it means the hours of daylight are changing or decreasing, right? We just got in saying since it's positive, that meant the hours were increasing. So if it's negative, it means decrease. So the question is said, when are the days getting shorter? That's the question. Okay, but that's what I want you to be able to do. I want you to be able to read H prime is less than or equal to 0 and translate that into words, knowing that that means, oh, okay, that's wants to know when the hours of daylight are decreasing. That's what it was saying. Okay, well, when is that? When do the days start getting shorter? You gotta know a little science, I guess, maybe. The summer solstice, June 21st, longest day of the year. Now, maybe I just know that because that's my dad's birthday, and growing up, that always made me mad that his birthday was on the longest day of the year. I thought that's not fair.
Why does he get more time?
Yeah, why does he get more time on his birthday? That doesn't seem fair. But that's the longest day of the year, summer solstice. So after June 21st, the days start getting shorter. So H prime would be negative until when?
So you basically, they were assuming.
December 21st, the winter solstice. On December 21st, the days start getting longer again.
Yeah, like on the
Right.
quiz, we wouldn't have to know information like
Yeah.
that. Yeah.
They're assuming that we knew
Probably.
that.
And so and then to really answer the question, it says what values of T. So you need to know when's June 21st, so you start adding up months, right? January is 31, February is 20. Whatever. You can add up, and that must be where the 171 came from. That 171 must be about June 21st. And then December 21st is 3 whatever. I mean, it's almost 353 or something like that. So between those time periods is when it would happen. But the most important thing you got to know from that is you need to be able to translate H prime. That you need to be able to do. That H prime would be the hours of daylight per day, or the change in the hours of daylight. That we got to be able to do. Okay? All right, because that's what H prime is rate of change. It's the rate of change of H. And since H was hours of daylight, H prime is the change in hours of daylight. All right, another one. Is that it? 54? Oh.
I know that.
Okay. All right. So you have this H equation. So we're not going to go all the way through all this, but this but there definitely could be something like this on the quiz. We'll go back and review it at another time. But this is really more about. It's kind of like the problem we did earlier, number 20. Just being able to use this equation, maybe graph, maybe plug some things into your calculator. It's really pretty straightforward. So they give you the H and they give you the V. So in part A, from what height was it thrown? Well, that's just in the equation. Which part of that equation is the initial height? But what number? The 74, right? That 8. I had it up here a minute ago. Oh shoot! No, I didn't. I lost it. It's the 74. You just look at the equation. No, that middle term is the initial velocity. That last term is the initial height. Okay. So I'd ask you that. It says, what was the initial velocity? So that's the 38, right? That just comes right from the equation. So you just kind of got to memorize that. All right. Was it thrown up or down? Up or down? Up. Why? 38's positive, right? If the 38 was negative, it was thrown down. Okay. So the 38's positive. That's how you can tell. Was the height increasing or decreasing? Okay. Here we go. Here's the calculus now. At 2, was the height increasing or decreasing? Where do you plug in it? Now, you could graph the H graph and get it that way, but let's say this was no calculator. This part could easily be done no calculator. How would you find out if the height was increasing or decreasing? No. Plug in a 2 to the velocity graph. If you plug a 2 into the H graph, listen, if you plug a 2 into the H graph and you get out, I don't know, 80, what's that tell you? It's 80, it just tells you it's 80 feet high at 2. It could be on its way up and be at 80, or it could be on its way down and be at 80. So we don't know if the height is increasing or decreasing
So
if we
need to
plug
find
into the
out
height
if
graph.
V is positive or yeah.
We need to know if the velocity, think about that. That's what we were saying before with east-west. Well, positive velocity is going east, negative velocity is going west. If you're talking up-down, positive velocity is up, negative velocity is down. Okay? So, yes, we've got to take the 2 and plug it into the V graph. If you get a positive velocity, we just got an answer in that in part A, or part B, right? We said, how do we know the ball was going up initially? Because the 38 was positive. That was its velocity. Okay? So it's the same thing here. Is the height increasing or decreasing? We plug it into H prime. If it's positive, it's going up. Negative, it's going down. Okay? D. At what time did the ball reach its maximum height? What do we say is the magic thing that happens when it hits its max? Slope is 0. So for part, was that D? So for D, you should have taken the V graph and set it equal to 0. take the v graph and set it equal to 0, because when the velocity is 0 means it has hit its peak. Okay? And then it says, how high was it? So you take that answer, so t is whatever, 7. That's when it hit its peak, and you put that where? Into the h graph, right? So you take the v graph, set it equal to 0, that's when its velocity is 0, that's when it's at its peak. Take the time that happened, plug it into the h equation, and that'll tell you how high it was at its peak. Okay? Now again, if you graphed the h graph and looked at it and traced, then you could answer a lot of these questions too. But I really want you to see the calculus part of this, because a lot of this you'll have to do with no calculator. So you won't get a look at a graph, right? So we got to understand these concepts. All right, the last one, E, says, how long was it in the air? Here's the ball. It was thrown from 74 feet. It goes up, comes back down. Isn't that the time we want to know? We want to know, when does it get back to the ground? How would we find out when it gets back to the ground without tracing on a calculator? Set the h graph equal to 0. Set the h equation equal to 0. Because we want to know when the h is 0. We want to know when the height is 0, because that's when it's back on the ground. Okay? So every one of those questions we can ask, or we can answer by just doing something with the h or v graph. We can plug into them, or we can set them equal to 0, and we can do them. Right? If we want to know when is the ball 20 feet off the ground, we set the h graph equal to 20. Right? When's it a maximum? That's when the velocity is 0, because that's when it's stopped. Okay? So now those are things we'll be working on more and more, and that'll get easier and easier to understand. But but that's some important things as well. All right, let's move on, because I do want to try to give you some time here to work on the homework today. So let's talk about section 1.5. I kind of hinted at it a little bit earlier today. With the slope. So we're actually going to be calculating some slopes today. All right? So you'll be using your calculators, from that standpoint. So let's first talk about one. Oh, here's one of your homework problems, for example. So, and yesterday, and I don't remember what this function was called. We'll just make something up. All right, so let's say this is the f function here, and we wanted to know f prime of -2. We wanted to estimate the slope of this graph, right? That's what that means. F prime of -2 means what's the slope of the f graph at -2. And all you had was this graph. You didn't have an equation. Okay, this is all you had. Well, what you would want to do is come into here and sketch a tangent line. Okay, and do a slope triangle. Do a rise over run. The next quiz, you will have to do this. Okay, there'll be a graph you'll be given. It'll ask for a derivative, and you'll have to do this. So this one looks to me like if we go over 1, and slope's always easiest if you do a run of 1. So I usually in my slope triangle try to extend it. Usually if you extend it a little farther, it's helpful. I usually try to extend it far enough where I can get a run of 1. That makes the slope easier to do. So it looks like, let's see, this is -3, so it looks like that goes up, I don't know, 0.8, 0.7 maybe. So to me, this would be a slope of about 0.8. Now, obviously, you're going to have some leeway there, aren't you? When I grade those, I'm going to look for your triangle. I'm going to look for your tangent line. I mean, if I just see a number that you just kind of pulled out of the air, that's probably not going to be very good. Okay? Now, if it happens to be right, I suppose you might be okay. But if it's off a little bit, and I don't see where you came from, that won't be good. So if I can see your line and see how you got it, and it's within reason, then you'll be okay. All right? So that's one way we can estimate slope at a point. Just draw the tangent line and do a slope triangle. So you'll probably have some of those. Did you kind of have to do that on today's homework? we had that position velocity graph. So I'm not sure if you had to. There was one there where they asked for like, yeah, like those, no, you guys didn't ask about this. I'm wondering if somebody doesn't have this question. There wasn't the equation of the tangent line. Was that easy? Wasn't there somewhere you had to write the equation of the tangent line? Was that 1450 we're talking about? Yeah, we got to know that for sure. Okay, so maybe before we go any further, let's do that. Which one was that? It wasn't 47.
Yeah,
40. Let's do 47. Let's do 47 because I've got a picture of that one here. Here's 47. Okay, and what's it say? It says, suppose f of 1 is 5. This we absolutely have to be able to do. Equation of a tangent line. You're going to get asked this over and over this year. So it says so this is the f graph right here. And they want the equation of the tangent line at this point. Or no, this is not f. This is, okay, this is the f prime graph. Thank you. So we don't even know what the f graph looks like. All we know is what the f prime graph looks like. And we're supposed to write the equation of the tangent line on a graph we can't even see. So we can't even draw the tangent line. But what do you need to write the equation of the line? Slope and point. Okay? That's all you need. The other point slope form that we've already been talking about. Well, look what they gave you. They gave you the point. So I would like for you to get in this habit. See, we can now use this notation. Now, in the past, what you would have done for a point is you'd have said, oh, I need 1, 5, and I need m. Well, forget m. We won't be talking about m anymore, right? What do we use for slope? F prime, right? We have a new notation for slope. So when we want the slope, we want f prime. So what I need is a point at 1, which there it is. They gave it to me. And I need the slope at 1. Don't we just read it right off the graph? Yeah, this is the f prime graph. So this y value is the slope on the f graph. So that's 2. So there's my point and my slope. So I got y equals 2 times the quantity x minus 1 plus 5, and I stop right there. So it is a very easy problem. You draw lines in there. Yeah, you don't need to draw lines on here because if you drew lines on this, you'd be finding what? F double prime. F double prime, right? This is f prime. If you do the slopes of this, you're doing f double prime, and that's not what we want. Because I think it's in the tangent line to f, right? It's in the tangent line to f, right? So that's all we do. I mean, but again, people get froze up on that. They find the equation of tangent line. Oh my God, oh my God. Find the equation of any line. You just need a point and a slope. So if they want it at 1, you need f of 1, you need f prime 1. F of 1's the point, f prime 1's the slope. And then you write it. And that's all you need to do. Okay. So that's some examples. There we found the slope just by reading right off the f prime graph. All right, so we might have to draw some tangent lines. Now let's go to our calculators. Go ahead and pull up this local linearity document that I sent you yesterday. Caitlin was yesterday. We won't make it. Sarah. All right, go ahead and go to the third screen. I think it's a third one. Yeah. All right, and so what we want to do here is we want, and I've been talking about this for a few days now, we want to understand locally linear means. Locally means in a small local region. Linear means line. When you have a curve, if you look at a tiny little space around a point, the line essentially becomes negative. So if you'll go on here, the bottom one where it says to zoom in, and just click and hold that down. And this goes slowly, but we'll kind of watch it go here. And as we zoom in and you can see that the x and the y values here are changing and getting smaller. We're zooming in at this point. That eventually we can see it's getting kind of straight here. That is bad, bad, bad. Yeah, just zoom in until it. Okay, that's really off. Okay. All right. Yeah. Yeah. Okay.
Tangent
Here.
line squiggles.
Let's come in.
A lot.
You do. Okay. All right. Let's try this. See if I can make this. All right. So now, I know. So now, here's the idea. Okay, this local linearity. So if we look at the calculator now, we've zoomed in to the point that this curve actually looks straight. So the idea is this: that if we are actually looking when we zoom in at that region right there, where the points that are on the line. Now, remember, what we're looking for is the tangent line slope, right? That's what we want, is the slope of that line. When we say we want the slope of the curve, what we really want is the slope of that tangent line. Okay? Problem is, we know the equation of the curve, let's say, right? We know what the equation of the curve is, so we know all the points on the blue curve. But we only know one point on the black line, and that's the one where it touches the blue curve, right? That point's the same. But we don't know any other points on the line. And to do the slope, I'm going to write my slopes this way, right? Since we're using function notation now. This is going to be our slope formula. y2 minus y1 is kind of old news, right? y2 minus y1, we're f of b minus f of a. Subtract the y's, subtract the x's. That's how we do slope. Now the problem is that if we pick 2 points on the blue curve, those are not on the line. But if we zoom in far enough, if we look really close to that point, the 2 points on the curve are practically on the line, right? That's the idea. That's locally linear. If we zoom in far enough and pick 2 points on the curve, they're essentially the same as 2 points on the line. So we can do a slope calculation and call that the slope of the line. At least be an estimate. All right? So if we want to actually do a calculation, okay, so thank you, Sarah, for that. So we're going to do our first slope formula right now. Okay? What I have here is, this is on my calculator. I just, or on this, I went ahead and I did a spreadsheet here. And I put in, if you look at this x column, I put in 0, pi eighths, pi fourths, 3 pi eighths, pi halves, and I went all the way to 2 pi, okay, by pi eighths increments, okay? So I put those numbers into my x column. And in the y column, I've put in the sign of the x column. So the y column here is sine x. So that's sine of pi eighths, that's sine of pi fourths, and on and on. Okay? Now, on this page here, I have graphed those points. So, sure enough, we get a sine graph, okay, as we would expect. All right. Now, in this column, what I did is that right there. Okay? Now look at that here a little bit. So what did I do? I took pi eighths, right, or whatever my point is, added 0.001 to it, so that means I just moved over just a teeny bit, did the sine of that, so that gives me my y, right? So that's like my f of b minus f of a. So I took my a1, so let's say it's pi eighths, and then I took 0.001 to the right of that, and I subtracted those y values, right? Sine of the right one minus sine of the left one. And on the bottom, I'd have the x's subtracted, right? And that'd be 0.001, that'd be the run. So this is slope, right? So this would be the slope of the sine graph. Now let's just guess here. If we look at a sine graph, okay? If we look at a sine graph, we might guess the slope is what then? Might guess that the slope is 1, right? Might be reasonable. And the slope should start getting less, right? Until they'd be 0 up here. Now let's look at that spreadsheet. Oh, looks like it's about 1. Looks like it's getting less, right? And let's keep going. If we were going to plot that, here in blue, start at 1 but get less, then what? Then they're negative and get what? Even more negative until here they're negative and getting what? Less negative, so it's going to be doing this. And then 0. This is getting pretty cool. This is kind of cool. I was waiting for it. Oh my God. Now I'm getting positive slopes and getting more positive, right? Until about there. Huh. Isn't that interesting? So you're telling me that if you plot the slopes of the sine graph, you get the cosine graph. Now if you can't, I'm sorry, you can't get excited about that. Something wrong with that. That is cool. If you plot, that's what we just did. If you plot the slopes of the sine graph, you get the cosine graph. Here's how you would write this. Here's what we just figured out. That if f of x is equal to sine x, then f prime of x is cosine x. It's like a slope formula, right? Cosine x is like a slope formula of the sine graph. All the outputs of cosine are the slopes of the sine graph. I mean, we just showed it right there. All those points that we had plotted there were calculated. Now, they were estimates, right? But they were really good estimates because they were 2 points really, really close together. Okay? You just learned your first derivative formula. All of chapter 3 will be about finding derivatives of functions. What's the equation? If you know you have this function, what's the derivative? So we just learned one right there. Okay? Let's do another one. What if f of x equals e to the x? Which is our exponential graph that looks like that. If f of x is equal to e to the x, I think I've got it here somewhere. Okay? All right, there's e to the x, and if we had tangent, so if we thought about that a minute, if we thought about plotting that, what kind of slopes would e to the x have? All positive. Keep getting more and more positive. Okay? So if we were to put that into this calculator, let's change this formula here. To be e to the a1, and let's copy that down. Okay, it's spreadsheet. Yeah, it's basically it's spreadsheet. Okay, so these would be the e to the x values. So they're positive and getting much more positive. Now let's go ahead and graph this. Okay, so this is pretty cool how it does this. It just sets the window on there. Okay, So there's those points, which is our e to the x graph, right? Okay, now let's do the derivative of that. So the derivative of that, so this column, instead of sine, we would make that e over, okay, a1 plus point. Okay, and then minus e to the, what, a1. All right, hit enter. What just happened? Yeah. Oh, wait, I gotta copy that. Kevin say something. Copy that down. What do you get? Close to the exact same number, but then again, we're just estimating, right? Because we did 0.001. So these slopes in that third column are not exact. But if they were, it's the exact same number. E to the x, and what people always ask, why do we do an e to the x? What's so important about e? Well, there are several things that are pretty cool about e, but one of them, and let's go ahead and let's graph this again. Okay, one of the things that's cool about e is it is its very own derivative. At every point on the e to the x graph, the slope is the same as the y value. The slope on the e to the x graph at every point is the same as its y value. So you just now learned your second derivative rule, and that's not true of any other exponential. 2 to the x, the derivative is not 2 to the x. Now it's close to 2 to the x, but it's got an added multiplier on it, which we'll have to learn about. But e to the x is the only function that is its own derivative, except, I guess, 0. The derivative of 0 is 0. But other than that, you know, something that's not just a routine kind of thing, but, okay, which is kind of a cool thing as well. All right, so there's just a couple of derivative rules, but the bottom line for you guys on your homework of what you're going to do is you're going to calculate some different slopes. So if I give you, let's take a look at some other things here. There they show you that. No, that's getting into some other stuff. So let's go to the book now. Sorry, those people watching the video, you're not going to see this, but we're going to be in the book on page, and let's go, let's look at page 48. Okay, so on page 48, we have a table. Okay, and it gives us some x values, gives us some x and y values of the function x squared. Okay, so if I was interested in finding, all right, so everybody looking at that, all right, we're looking at the table on page 48. Okay, back to this. So if I ask you to give me an estimate, so let's say we didn't know that was x squared. Let's say we did not know what that function was. All we knew was that table. And I asked you for an estimate of, is it negative 1.5? Are those x's negative? Okay. If I asked you for an estimate of f prime of negative 1.5, and all you had was a table, you're going to just pick 2 points and do a slope. Now, what 2 points would you pick? The ones closest to 1.5, right? You want to get as close as you can. Now, in a table, you don't have a lot of choice. Now, so one thing, you could take f of negative 1.5, and the other one could be, what, negative 1.6. Now, some people might argue, hey, why don't we take one on each side? That's perfectly legitimate. You could take 1.4, negative 1.4, and negative 1.6. You say that might be a little more accurate. And you're right, it probably would be. So why didn't we do that on that calculator program? Well, if you get close enough, it doesn't matter, right? If you zoom in far enough, it doesn't matter if you take one on the left, one on the right, or if you take one right at 1.5 and then take one to the right. Usually, just the calculation is simpler for some stuff we'll do later. So we usually take the one we're looking for and then one right next to it. But if you get in close enough, it doesn't matter. So this, I want to see this on your paper. I want to see that written out. Okay, so when we're doing it on the next quiz and you're having to do a slope calculation, I want to see your y's and your x's that you're using. Okay, so now from the table, what's f of negative 1.5? 2.25. Okay, what's 1.6? 2 point what? 5.6. Okay, and down here, of course, we have 0.1, right? And so we go ahead and what did we get there? Negative 0.31 divided by 0.1. Did I do that right? And that would be negative 3.1. So that would be our slope estimate. So you're going to have some problems where you're going to sketch a tangent line and maybe do a slope triangle like a rise over run. You're going to have a problem where you have a table of data, and so all you can do is do a slope calculation. Just pick 2 points as close as you can in the table.
For that, would you want me to leave that answer and just say the slope is approximately?
I would leave this answer right here. Leave this answer right here, okay? And then you also may get some where they give you an equation. If you have an equation, okay, then you can pick, where you want to go. Let's look at an example here. Number 14. Number 14 on page 52. Okay? Number 14 on page 52 says that your function is sine x, and it says give an estimate of f prime of 3. Now, that's part B. Part A says find a viewing window centered at 3 where it looks straight. Remember when we did that yesterday? Okay, so what you want to do is zoom in, zoom in, zoom in at 3 till it looks straight, and then trace. And just pick 2 points that are really close. Let 3 be one of them, and maybe the other one is 3.001, right? I mean, that's all we're talking about. Right? They want an estimate of f prime of 3, so on your calculator, you're going to graph sine, you're going to trace the 3, you're going to zoom in till it's straight, then you're going to just trace at 3, trace at 3.01, you're going to write those numbers down, you're going to do a slope calculation, just like that. And that'll be an estimate of the slope of 3. So that's a lot of what this homework section's about, is actually calculating some of these slopes. Okay? All right. I only have one more thing to show you, and this is just 30 seconds, and we talked about it a minute ago. If you get this graph right here, oops, okay, look what happens if you zoom in. If you zoom in at the V of a V graph, right? Remember how we talked about when you zoom in, it turns straight, and that'll be the slope? Well, that's one of the reasons the slope's undefined at a point like this. Because you can't zoom in, it'll never straighten out. I mean, you keep zooming all day and it'll still look like a V, right? So whenever you have a sharp point like this, the slope, we say, is undefined. And then they also give you one in your book, if you would turn to page 50 real quick. Another type of graph where the slope is undefined is if the tangent line would be vertical. Now this is a function, okay? This is a function, but there is one point right here where the tangent line is vertical. And vertical lines, of course, have an undefined slope. It passes the vertical line test. It only touches that, it passes the vertical line test, but there is a place there, just in an instant, where the vertical line would go, the tangent line would go vertical. So at that point, we say the slope's undefined. So sharp points and vertical tangents, undefined slope. All right, 1.5 homework is what you got for tomorrow. And for Monday, now you'll have another assignment tomorrow that will be for Monday, but this is a kind of a short little article to read. And you're going to write me a paragraph or so. You can type it or handwrite it, I don't care. That's a good question. Let me think about that and see how we can do it. You can probably email it or Google Doc, email it to my Comcast account. Yeah, that would be. We should do that. So let me think about the logistics of that, and we'll, because I haven't done it before, so we'll talk about that. But I think we should be able to do that. That's not due till Monday. But just a reaction. Not a summary, I don't want a summary, I want a reaction to what's in here. I think you'll have one.
How you feel?
Yeah, I think you'll have a reaction. It's kind of thought-provoking, I think. So just read this article and write me a paragraph or so, 2 paragraphs, whatever. I mean, some people write more than others, but just your reaction, agree, disagree, what'd you find interesting, that kind of thing. Okay?
And that's due Monday.
That's due Monday. So for tomorrow's 1.5.
Oh, that's small.
It's pretty short. Yeah, it's not too bad.
And then for tomorrow, 1.6.
You're gonna be on tomorrow. Yeah, tomorrow, the first one, 1.6 day one. It says there's like 3 days we're gonna be on that section. So
You're missing a good day.
I just watched the video.
I'll have a video. Okay.